Okay, well, good morning and happy Friday. Thought we'd get started with maybe a clicker question here. This one being about kind of, which condition is violated for using the central limit theorem, right? So the question is, read the following scenario, determine if any conditions have been violated. Okay, so you say, I don't know, you decide to take a survey of, I don't know, dog owners, okay? And you manage somehow, I don't know how, but you manage somehow to obtain a random sample of 200 dog owners. You ask, are your dogs spayed, neutered? All right. Okay. And you get 96% of dog owners answer yes to your question. Okay. And so, can we use the CLT to estimate the sampling distribution? Let me see if I can copy this over. I need to shrink this text just a tiny bit. Okay, so you can talk to your neighbors about if any conditions have been violated, yes or no. And I'll start with that. Okay, and yes, when we check the answer, the correct answer is B. As we go through the problem, it says we were somehow able to get a random sample, so condition A has been met. And as far as the large sample condition, we have 96% of dog owners say yes. So we need at least 10 yeses and 10 nos. So in this case, we are not provided counts, but we have to check, is n times p greater than 10? Okay, and so in that case, we do 200 times 0.96, and we get 192. So yes, that is bigger than 10. But if we check n times 1 minus p, we have 200 times 0.04. And we only get 8, and that is not bigger than 10. So condition B has been violated. As far as the big population, we have, in our case, the population is all dog owners. And so all dog owners, we would have to check is 200, our sample size, times 10. That is 2,000, and is our population bigger than 2,000? And the answer is yes. Greater than 10 times our sample? Yes. So that condition is met. So met, and this one is violated. Okay, let me, I guess we can do one more of these types of questions, just to make sure I got a handle on this. Just Okay, so we'll do one more. All right, okay, so this time we're going to say decide to take an opinion poll, regarding, I don't know, healthcare law. All right. And so, we'll say that you send surveys to, we'll say 600, okay, so opinion poll regarding healthcare law in, we'll say in your local town with a population of 10,000 people. We'll say 10,500 people. Okay. You send surveys to 600 randomly selected residents in the town. Okay. Get a response from 250 of them, and of those responding, I'll say 120, I don't know, we'll say, 105 support some proposed legislation. Okay. All right, can we use the central limit theorem to approximate the sampling distribution? Okay, so this is the question here. Again, you can turn to your neighbors if you think any conditions have been violated. All right, let's take a look. All right, indeed, I would say condition A has been violated. Okay, and so when we look at it, we have a population of 10,500. We've selected people at random, but the problem is we only get a response from 250 of them. Okay, and so this, we're not getting 100% response rate, so not 100% response rate. And so that's going to induce non-response bias. Okay, and so condition A has been violated. And we can go through the other conditions, but really, as soon as we find out that the random and independent condition has been violated, there's no real sense in even trying to do, well, using the central limit theorem. You might be able to use the data for something else, but it's a lot more tricky. Okay, as far as the large sample condition, okay, so technically our sample size now, we have basically 250 responses, and we have 105 that say yes, which mean we have 145 that say no. Okay, both of these are bigger than 10. So we're okay as far as the large sample condition. And then for the big population, our population, we have 10,500 people. And our sample, whether it was the 600 or the 250, technically our sample is only 250 responses. If we multiply that by 10, we have 2,500. Our population is bigger than 10 times our sample. if we had a 100 response rate, we would have a sample of 600, and our population is still bigger than 10 times our entire sample. But so that condition is met. But again, our random independent condition has been violated. And this is the real crux of the problem when we are talking about doing opinion polls and surveys. It's truly difficult to get a random sample. And I just listened to a podcast about, if you ask a person a question, okay, they are more likely to give you a response that sounds better than what it actually is. Even if you're never going to interact with this person again, people are just accustomed to lying. Then and there's no incentive to tell the truth, and they don't want to be embarrassed by giving some the true answer. And so basically the researcher was saying, if we look at Google search data, that's what reveals the true nature of people. So if you ask someone straight up, like, do you have racist opinions, everyone's going to say no. But then if you look at what they are searching online, it's more likely to reveal these things that people are generally not proud to share publicly. So okay. So you can expect to see questions kind of like this on next week's midterm. So we have a midterm 1 week from today, test 2. It's only 12% of your grade, so it's not. I don't want to say it's not a big deal, but don't stress out too much. And it's just grades in a class anyway. So. All right, so you can expect to see questions like that, and we'll continue on here. And so so the midterm. Let me just briefly talk about the midterm, and I'll talk about the midterm again next week. But the midterm will cover chapters 5, 6, and the first half of 7. Okay, so this is all probability. I would say this midterm is a little bit more calculation heavy. The first midterm had a little bit more definition and conceptual stuff. There's still going to be some definition and conceptual stuff here, but I would say, a bit more calculation heavy. All right, so, keep in mind, Chapter 5 was all about probabilities. Chapter 6 was probability distributions, including the normal distribution and binomial. And Chapter 7, or at least the part 1, is about sampling distributions. Okay. Sampling distributions and the central limit theorem. Happens to the best of us. Okay, and so that's what you can expect to see on the midterm exam. 45 minutes and whatnot. Okay. All right. Well, I guess I'll just talk briefly a little bit more about sampling distributions and the central limit theorem, and then I'll start introducing maybe the second part of Chapter 7. Okay. All right. So far, what we've said is that the sampling distribution of p hat can be approximated with a normal distribution. You know, as long as the conditions are met. Okay, so as long as those conditions that, you know, we've asked questions about, as long as those conditions are met, the sampling distribution of p hat can be approximated with a normal distribution. And we might say something like p hat follows a normal distribution with mean p and standard deviation p times 1 minus p divided by n. Okay? When we are talking about the standard deviation of a sampling distribution, we might also call this the standard error. All right? So the standard error also abbreviated SE, is the standard deviation of the sampling distribution. Okay? And so if we think about what the standard deviation means, the standard deviation is a measure of spread, right? So the SE is the measure of spread, tells us about the spread of the sampling distribution. And if we think about what the sampling distribution tells us, the sampling distribution tells us about random samples and how they relate to the population, right? So the sampling distribution tells us about kind of the relationship, or I guess about the distribution of p hats being the kind of sample statistics about the distribution of p hats around the population parameter p. Okay, so we can think of the standard error as a way to kind of describe how good of an estimate p hat is for p. So another way we can standard error as a way to kind of describe, I guess, what is the word I'm looking for? Describe the precision of using p hat as an estimate of p. Okay, so kind of, I think that on our first day of class we talked about what is the why do we bother studying statistics, and we said one thing that we want to use statistics for is to make conclusions about the population based on a random sample. All right, and so what we're able to say now is that when I see a random sample, we can observe the sample proportion, and this should give us some information about the population proportion P. Okay, and this is going to begin the kind of our second half of chapter 7. All right, and so I'll just introduce this idea here. And so so let me just say, earlier when we were talking about sampling distribution problems, okay, so earlier for sampling distribution problems, I would give you information about the population. Okay. Give you information about the population. So, for example, I told you that the population was 30% orange pieces, right? Okay. Or, I could tell you in the population, we have some proportion, right? So I told you the population was 30% orange pieces, so this means I gave you the population proportion P. Okay, so this I'll just put, so on the midterm you can expect to see problems where I give you information, I will say something like, the proportion of whatever, the proportion of, something, orange people, we'll do, red candies is blank, 25% or something, okay? And I'll say something like, if we select a random sample of 100, what is the probability that, less than 20% are red, or something like that, okay? And you guys should be able to answer this, right? You just say, okay, well, p hat comes from the normal with mean p and square root p times 1 minus p over n. And so you have p hat comes from normal with mean 0.25 and square root of 0.25 times 0.75 over 100, et cetera, and you do your problem, right? You get your z-score, and then go to the table. So you can expect to see questions like that on the midterm. This is what we've done so far. I gave you the population information, and I asked you a question about a random sample. But in real life, we generally don't have this population information. Okay? The whole point of statistics is that we don't know what the population looks like, and we've only seen a sample. And so, can we reverse this process? Sort of. Okay? If I only see the sample, can I make conclusions about the population? That's what we want to do. Okay? So far we've saying, okay, if I know the population, I know the sampling distribution, I can answer questions about the sample. Can we go backwards and say, if I only see the sample, can I then make inferences about the population? That's what we want to know. Okay? So generally, We do not know what the population looks like. And so here's our question. The question now. If we observe only a sample, can we make inferences about the population? Okay? So for example, we'll keep using this tub of candy example. All right, so in here we've got Skittles, and we'll say, you take a scoop of Skittles out, okay, and you dump them out and you count, we'll say 150 pieces of candy. And we'll say that 25 of them, 25 are green. Okay? So the question is, what is the proportion of green candies in the bucket? Okay, that's what we want to know. Okay. So this time we don't know what the population looks like. Instead, we are looking at just a sample. Based on the sample, can we make conclusions about the population? Okay, and this can be generalized to anything, right? Here we're talking about Skittles and how many are green, but this could be about the American population and what proportion in the population have this opinion, or it could be whatever you're interested in. All right. So if we look at this in our sample, the information that we have is n is 150, x is 25, and our p hat is 25 divided by 150, or what is this, 1 and 6, or 0.1667. So the proportion I've observed in my scoop is that it's 1/6 green. And what does this tell us about the proportion of green candies in the bucket? Is the proportion of green candies in the bucket also 1/6? Or could it be higher than that, lower than that? If we counted them all, like the only way we're going to get the actual proportion is if we dump out the entire bucket and we count every single piece and we count exactly how many are green, right? That's the only way to get the true value of P. And maybe I'll write that down. So keep in mind, the only way to get the true value of P for the bucket is to dump out the entire bucket, count all the pieces, and count how many are green. All right, and so you might have a couple thousand pieces of candy and several hundred that are green. That's the only way you can get the true proportion P. But if I look at just a scoop, can I make inferences about the population? That's what I want to know. Okay? So what do you think? Yes? Maybe? All right. We'll put that thought on hold. And now I'm going to draw a little picture for you and tell a story. Okay. All right, so let's say, you see some picture here. Someone shares a picture on, all right, and what do you see? You see, this is a picture of it's a dog, okay, and the dog is on a football field, and then I don't know, some. All right, okay, and the question is, dog going for a walk. But it says, where is the owner? Okay, and the owner is invisible. All right, that's the problem. All right, the owner is invisible, and the leash is also invisible. All right, what is this ridiculousness? Okay, it's also invisible and elastic. All right, this is very important though. All right, for the illustration. Okay, so the owner is invisible, the leash is also invisible and elastic, and what we see is the dog is located at the 30 on the football field. All right, so what can we say about the owner? Okay, well, let me tell you a little bit about the behavior of the dog. So we understand the behavior of the dog. Okay? Generally, the dog likes to stay close to the owner. It doesn't like to strain too hard against the leash, okay? Okay, and let's say we've studied the behavior of the dog so much that we can say, approximately 68% of the time, the dog remains within 1 yard of the owner. And approximately 95% of the time, the dog remains within 2 yards of the owner. And what's the last sentence I'm going to write? I would say approximately 99.7% of the time, the dog remains within 3 yards of the owner. Okay. And so, if we see the dog at the 30, what can we say about the location of the owner? So we see the dog at 30. What can we say about the owner? Can we create a range of where we think the owner is? Yes, and all right, what would you give for a good range of where you think the owner might be? So I can make a statement something like, I'm 95% confident that the owner is between where and where? 28 and 32, right? So I can say something like, I am 95% confident if the owner is between 28 and 32. Does that make sense there? All right. Does that guarantee that the owner is between 28 and 32? No, the owner could be at 33, okay? But if the owner's at 33, then that means this picture was taken at one of those rare times where the dog was kind of straining against the leash, right? Could the owner technically also be at 34? Yeah, the owner could be at 34, and this is one of those very rare times where the dog is straining really hard against the leash, okay? But, you know, based on what we know about the behavior of the dog, we can say something like, I'm 95% confident that the owner is between 28 and 32, okay? Or, you know, somebody says, well, I want you to be more than 95% confident. You can say, well, I can be 99.7% confident that the owner is between 27 and 33. I can be more confident by giving kind of a larger zone for where the owner is, right? And, you know, I could say, you know, I'm 100% confident that the owner is, you know, somewhere on Earth. You know, going from negative infinity to positive infinity or something like that. Or, you know, if there's like an enclosure, like a brick wall that the elastic leash can't stretch against, then, you know, you could say I'm 100% confident the owner is, you know, within this enclosure or something like that. But that's not useful, right? So we can say, you know, we can get a narrower zone and have a reasonable level of confidence, such as 95%. Okay, so why did I bother telling you all of this? Okay, well, this is kind of it's supposed to be an analog to what we're trying to do with the confidence interval, okay? We can see the dog, and the visible dog is similar to the p-hat, the sample proportion that we observe, okay? The visible dog, so we can observe the sample proportion. That's kind of the what the dog represents. Meanwhile, the invisible owner is like the population proportion that we don't know, okay? This is the unknown population proportion. The unknown population proportion. We want to know, where is the owner? Where is this population proportion if we can only see the sample proportion? Based on the sample proportion, what can we say about the population proportion? Okay? And this behavior of the dog, this is basically the central limit theorem, stating that p hat follows the normal distribution. Okay? So the normal distribution, the central limit theorem says that whenever you take a random sample, 95% of the time, that p hat you get is going to be within 2 standard deviations of the mean. Or 68% of the time, that p hat is within 1 standard deviation of the mean, or you know, whatever you want to say, with the normal distribution. And so, because we understand how the normal distribution works, because we understand the behavior of p hat in relationship to p, even though I don't know the population proportion, if I observe p hat, I can say something like, I'm 95% confident that p is somewhat close to the p hat that I've observed. Okay. So we're going to say that, so the premise of the confidence interval by observing just P hat. We can be confident that P is nearby because the central limit theorem tells us that random samples produce P hats near P. P hat's close to P most of the time. Okay. Yeah, again, because it is random, it's possible to end up far away. But most of the time, the P hats end up close. All right? So we can say something. So we're going to just begin. This will be our, quote, loose confidence interval, which is not going to be our formal one, which we'll kind of define on Monday. We're going to just start off with something along the lines of, I am 95% confident that the population proportion P is within 2 standard deviations of the sample proportion P hat. Okay. Or we can also rewrite it as, I am 95% confident that P is between P hat minus 2 standard deviations and P hat plus 2 standard deviations. Okay, and we will formalize this in a little bit. Okay, so this is still informal confidence interval. Okay, the formal one will come on Monday. But we'll end here for today, and we will see you guys on Monday. So have a great weekend.